In the laser industry, specifically,
it has changed dramatically.
The field of biophotonics was just getting started.
The first instrument that I bought was a microwave spectrum analyzer.
It's time to shed light on our universe. This is All Things Photonics, a podcast about the physical science of light. Join us as we explore the latest in lasers, optics, spectroscopy, and microscopy. Each episode, you'll hear from leading voices from across the photonics landscape. We're brought to you by Photonics Media.
This is Associate Editor Joel Williams. Here are this week's top stories. At the National Institute of Standards and Technology, researchers proposed an approach to large-scale artificial intelligence that focuses on integrating photonic components with superconducting electronics as opposed to semiconducting electronics. The work has the potential to boost the function and scale of silicon-based AI chips and optoelectronic advancements as a result. A research team at Tianjin University developed a method for analyzing water-rich samples using time-domain terahertz optoacoustics. The method overcomes a bottleneck that prevented the use of terahertz radiation in the investigation of biophysical and biochemical processes deep within tissues. Researchers from Tokyo University of Science and Osaka University used near-infrared hyperspectral imaging to quantitatively analyze the distribution of lipids in a mouse liver. The ability to do so, using hyperspectral imaging, charts a course for non-invasive diagnostics of non-alcoholic fatty liver disease. A device constructed from low-cost materials that exhibited high stability at temperatures as high as 200 degrees Celsius is capable of imaging light waves in the shortwave infrared region. Scientists in Europe developed the organic device by combining a squarane die-coated flexible substrate with an OLED. And finally, researchers from Technion Israel Institute of Technology demonstrated an approach for obtaining images of evanescent waves that uses nonlinear wave mixing. The microscopy method allowed the researchers to fully reconstruct the electromagnetic field of the evanescent waves and to perform real-time monitoring of wave pattern changes. Up next, news editor Jake Saltzman is joined by Dartmouth College's Eric Fossum, who is credited with developing the CMOS image sensor. I'm Joel Williams, and you're listening to All Things Photonics.
Our guest today is Dr. Eric Fossum. Dr. Fossum is a Queen Elizabeth Prize laureate, a recipient of the Queen Elizabeth Prize for Engineering in 2017, and winner of a Technology and Engineering Emmy Award in 2021. He's also won an Edwin H. Land Medal from OSA, and his accolades include an Inventor of the Year recognition from the New York Intellectual Property Law Association in 2010, Society of Motion Picture and Television Engineers Camera Origination and Imaging Medal in 2014, and 10 years ago he was inducted into the National Inventors Hall of Fame. Dr. Fossum invented the CMOS active pixel image sensor used today in almost all cell phone cameras, webcams, many digital still cameras, and throughout medical imaging technology. Dr. Fossum, thank you for being on with us.
It's my pleasure. Thanks for asking.
So, I mentioned the CMOS technology and your heavy involvement with it as inventor of the active pixel image sensor. Can you take us back 30 years or so? You're working at NASA JPL, and the CMOS process has pretty widespread microprocessing applications. But the track that CMOS technology is traveling really isn't parallel to that of CCDs, which is significant as camera technology is advancing in that time. What's holding CMOS sensing capabilities back, particularly for consumer applications?
In the early 1990s, there were a few people working on CMOS image sensors, and active pixel devices have been explored as early as the 60s. But most of these devices, or all these devices, I should say, suffered from a lot of temporal noise, fixed pattern noise, and instabilities in the early days in just the MOS process. But by 1990 or so, VLSI Vision in the UK had been producing passive pixel CMOS sensors, but unfortunately the performance was pretty poor still, noise in particular. And so they were just kind of relegated to the toy market, like Barbie Cam and that sort of thing. And NHK, the National Television Laboratory in Japan, was still exploring MOS active pixel sensors, 3T type, as we can get to later, but they also had pretty poor performance. So, yeah, it was quite a bad place to start to introduce CMOS image sensors. I remember Savas Chamberlain, who founded DALSA, for example, asked me why I was working on this technology when everybody knew it didn't work well at all. It had been tried before, and I was just wasting my time.
What did you tell him? I mean, what was, for you, what was the motivation? What was the impetus for evolving this technology?
Well, I told him I thought he was wrong, that it would work. And I think part of what he missed also was the timing of the situation, the fact that low power was starting to become incredibly important, as was form factor, and cost as well as a barrier to mass production as we see it today. Well, also we made a bunch of innovations that made it work a lot better than anything previous.
So for those unfamiliar with your 1993 paper that in many ways kickstarted this notion that, not only are our CCDs going to have a dance partner, but in fact they're going to have a successor. And we know what this successor is going to be. You didn't pull any punches. The paper was titled Active Pixel Sensors, Our CCDs Dinosaurs. Was it clear to you then, as has proven to be fact in the last almost 30 years, that by overcoming this fundamental need for a very clean transfer of charge, that's the CCD problem that has necessitated refining usability at high frame rates and at all temperatures too. I mean, were you thinking that this would completely innovate the way that imaging is done?
Yeah, actually, it was clear to me that the potential was there, that this was a very good path to go down. And it was very frustrating that almost everybody else in the image sensor world, my friends, my colleagues, didn't see it the same way I did. And so it was like trying to get a giant oil tanker to change course. It was very difficult. I think from a power point of view, as I just mentioned, and form factor, two big things. And then also speed and for space, radiation resistance, radiation hardness, and also scaling up array size where you read out more pixels per second, essentially, and make bigger chips. All of those issues were bad for CCDs, and they were all great for this CMOS image sensor with intrapixel charge transfer device that we had invented at JPL.
What was the motivation in the very first place to work with CMOS? Was it strictly I see the potential, let's pursue it, or was there something else? Yeah, actually, there was something else, and something else was that I proposed to JPL to do a very exotic active pixel device in our micro devices lab, and they rejected my proposal as being way too expensive. So I was trying to figure out how can I still demonstrate some of these ideas and advantages without having access to my own fabrication lab. And I decided, well, let me try to explore using a standard CMOS image sensor process because it's inexpensive and I can access it. I just have to figure out how to do that with a standard CMOS process. And that was where this intrapixel charge transfer concept came from. And it worked right away. So the motivation was I didn't have any other choice but to try to do it in a low-cost process. Are you, not all of our guests who have faced similar situations, in their areas of technology will admit to this or even speak to it in a lot of cases. But were you motivated by the doubts, by the rejection, by the clear limitations and people's eagerness to point them out to you?
No, I wasn't out to do it just because I wanted to prove that I was right. It was because I honestly felt I was right, and it was the right way to go, and that it would be a shame not to explore that more. Also, I was motivated to do the job that I was asked to do for the space program, which was improve the performance of image sensors in outer space. We had to pursue that goal as best we could. So I would say that was the main motivation at the time, was really a little bit more altruistic.
Dr. Eric Fossum is our guest on All Things Photonics. One of the most influential singular advances to APS technology, and within that CMOS deployment, involves the incorporation of the PIN photodiode. And this was in the literature, really mid-90s. In doing research, I noticed. This isn't a new integration, but it is sort of a lingering one. In 2014, for example, you and a colleague co-authored a review of pin photodiode performance for image sensors. Can you explain for our audience what we're talking about with this notion of PPDs and the significance to APS technology?
Well, actually, the pinned photodiode was invented at NEC in a team led by Nobu Teranishi, who's also a friend of mine now, as a no-lag photodiode for interline CCDs. And it solved an important problem they had with interline CCD of regular photodiodes, which suffered from lag and a few other things, including noise. But he invented that and published that in 1982. And so it was pretty clear that this same sort of device would be very useful in an intrapixel charge transfer CMOS image sensor. But the trouble was is that when they used it in CCDs, that device required like 20 or 25 volts to get the charge out of the pixel photodiode and into the CCD shift register. And when we teamed with Kodak in the early 90s to develop that for our CMOS image sensor, because Kodak had figured it out for CCDs already, Kodak had to figure out how to make it work at 5 volts, which was a very difficult process to get good transfer from the photodiode to the CMOS output amplifier in each pixel at such a low voltage. But the key thing for a pinned photodiode is that it's a fully depleted region. That means that when you transfer the charge out, it's complete charge transfer. There are no electrons left behind that can cause lag. And also it reduces the noise because there's no uncertainty that you haven't transferred all the charge out of the pixel. And so that's the key thing, is complete charge transfer. And that coupled with correlated double sampling and the in-pixel floating diffusion amplifier is what really makes these devices work so well today.
Are you surprised by the progression in the current state of imaging and photography in contemporary society? You know, the journey from camcorder to selfie is not linear. It is ubiquitous. How do you feel about the contributions your work continues to make? Because they're certainly ongoing. They're certainly prominent, maybe now more prominent than in the past, and they're really impacting widespread areas of technology.
I know. It's mind-blowing to me. First of all, I wasn't even sure that even though there were a lot of advantages to the CMOS image sensor technology, that it would actually happen, that we could change the course of that supertanker out in mid-ocean. But it did. It took a while, but now it's everywhere, and everything I had hoped it would be, ubiquitous, low cost, small form factor, all those things have come to pass. And that's just made it incredibly useful for all kinds of applications, from fill cameras to automotive ADAS systems, and drones, and medicine, and of course web cameras, or zooming today during the pandemic, using that technology, and many other things. So I find it mind-blowing, in a word. I can't really wrap my head around it all the time, but it's also very satisfying to see people have fun with the technology and taking pictures or selfies or pictures of their cats or kids and sharing them.
I want to ask you about that. That certainly doesn't seem to me to detract from some of the the late nights in the lab, the heavy thinking that went into developing the technology. How do you view that? I mean, a big application of your work, and for better or for worse, is people taking photos of their cats. I mean, how does that resonate with you?
Like I said, it does feel like a waste of an awfully good technology just to indulge in narcissism and taking photos of yourself. But you know what? People are having fun, and I can't imagine anything better coming out of something that we create than giving people a little bit of joy and pleasure and comfort and being able to share those pictures with friends and family.
So to be clear, though, that was not there was not in 1990 a thinking that we need more felines on this thing that's going to become the internet. That was not a motivation at the time.
No, but actually, the first time we ever heard about putting this kind of technology into a phone, as a camera phone, was an application that had to do with, and this is a totally true story, was that as a gimmick for Japanese girls to share the shopping experience with their friends. And that, I thought, was a total waste of a perfectly good space technology. But the customer is always right, and gosh, look what happened. 6 billion cameras made every year or something like that now.
Yeah, another critical technological advance. Dr. Eric Fossum is our guest. He joins us from Dartmouth Thayer School of Engineering. One of the conversations we really look forward to having with each of our podcast guests pertains to this confluence of industry and academia and research. As someone who's started companies and who's run companies and today serves as Dartmouth's Associate Provost for Entrepreneurship and Technology Transfer, what are some of the benefits of this arrangement of industry and academia in this industry, optics and photonics? Because not every industry has that type of arrangement.
Well, there are a couple of different sides to that coin, I think. And the one that I see being in the academic job right now is that as a research university, we get a lot of funding from the U.S. government, taxpayers. And I believe there's a social compact that says that one of the things we do with the outcome of our research is transfer our technology to benefit society so that society benefits from it. So I think it's very important to do that, and we try to make that as seamless as possible at Dartmouth and put the faculty member first and put the aim of transferring the technology first. And then, it's nice to make money along the way too, but the main thing is to fulfill our obligation under what I think is a social compact. But it's also very important, especially for me, to get that input from industry about what are the outstanding problems, what are the things that need to do next, what are the big challenges, and maybe even for academics to be able to see what those challenges are from various points of view in industry and kind of fuse them together for new kinds of solutions that really push the boundaries. It's also important to, and we're working on this at Dartmouth, we're not there yet, but I really want to make it very easy to work with industry for our faculty members and to make it easy for industry to reach out to those faculty members.
What are some of the obstacles? You say you're not there yet. What are some of the restrictions that are facing you and your colleagues and your students right now?
Well, I think there's lots of, academia has a lot of momentum and a lot of history. One barrier has always been that doing anything that is applied is somehow taints the science of pure academia or the ivory tower, which I think the new generation of faculty that are coming in don't feel that way at all, but there's still a lot of more traditional faculty members that still feel that way. So there's that sort of bias in academia. Then there's also issues regarding intellectual property and how that gets shared and who benefits from intellectual property. And frankly, industry often tends to be a little bit uptight about that. So it's got to be a win-win situation, both for the university and for industry.
I have this in my mind as a tech transfer question, but it may well be an intellectual property question. And what advice do you give those working in academia or budding entrepreneurs about the tech transfer process, this whole process of developing a technology and moving it forward, moving from academia to industry?
Well, one of the things I like to say is that it's a full contact sport. You can't just write your invention disclosure, attach your latest paper, and send it to your tech transfer office and expect miracles to happen. That somehow everybody will realize how great your idea is and flock and license the technology and you're going to make lots of money. That is just not going to happen, except in maybe some rare cases. You have to be very proactive about it. You have to really understand what the problems are out in industry. You have to promote, I don't mean in a bad way, but really make sure that people understand what the benefit of your technology is, your new idea, and how they might use it. It may be that you have to start your own company in the end, because nobody is more motivated typically than the inventor themselves to see that their idea grows up and matures and survives. And that means you have to put the effort into it. It's not going to happen by itself.
Our guest is Eric Fossum. He is a winner of a 2021 Technology and Engineering Emmy Award. We've talked about CMOS and CCD and taking pictures of cats and shopping. Let's talk about quantum image sensing. In as much or as little depth as you'd like to go into, what is it? And I guess within that, what are some of the differences between how QIS is performed and how CMOS sensors and CCDs obtain images?
Generally, I'd put it into the category of what have you done lately for the CMOS image sensor technology and what can we do better. But I was challenged by a friend of mine who was writing a book on was asking, so what's next? What's the ultimate limit for image sensors? And after thinking about it for a while, and this was 10 or 15 years ago, I came to the conclusion that, boy, the limit, we're going to have really tiny pixels that might be able to only store a couple of electrons, let's say one electron, and we're going to have to be able to count every photon and convert it to an electron. And we have to read out those electrons, and we're going to have lots and lots of pixels. In fact, they're so specialized pixels, actually I wound up coining a phrase for them called a jot, which comes from the Greek smallest thing. And we're going to have, 1 billion jots on a chip, and we're going to read it out at like 1,000 frames per second. We're going to have all this binary data. It's going to be like a scene out of the Matrix or something. And then we're going to use computational imaging to create the visual images from that data that we collect. So that was great for vision. I didn't get a chance to actually work on it heavily until I got to Dartmouth in about 2010 or 2011. But in fact, we've been able to solve a couple problems that existed. One was, can you detect a single electron in silicon reliably? And the answer is yes, you can. And we can do it without using avalanche multiplication. And then another question was, can we build really tiny devices that do this? And the answer to that is yes. We can build pixels that are submicron in size, that are sensitive to single electrons. And can we think about putting them in a billion on a chip? And I think the answer to that will be yes. Certainly tens of millions has already been demonstrated. And then can we do it inexpensively in an existing process? And I would say that that's also been proven to be correct. We are able to make those devices in a mainstream CIS process with our partners at TSMC.
You mentioned Avalanche Gain and developing applicable alternatives to it. What's the impetus there for bypassing Avalanche Gain, particularly in megapixel image sensing?
Yeah, about the same time frame as I was thinking about this quantum image sensor and doing nothing about it, people were working on single photon avalanche detectors, SPADs, and they've moved along in the interim also and just recently reached the 1 megapixel level. But the problem is that when you use, and by the way, SPADs are fantastic devices for very high-speed image capture, no doubt. You capture a single photon and detect it in nanoseconds. But when you're using avalanche, you need high electric fields inside the pixel. So you're really stressing the silicon. It's going to be very susceptible in terms of dark current, dark count rate to any impurities or defects in the silicon. So I anticipate there will be relatively low manufacturing yield. Pixels have to be have lots of isolation around them, so they tend to be larger pixels, 10 microns, maybe a bit smaller. Whereas we're already submicron with our first quantum image sensor devices. The long-term reliability questions aren't really clear yet. And then pixel size is very important for resolution, so it's hard to have high resolution and large pixels at the same time without getting very, very expensive. And then the last thing is that these SPAD devices are kind of Geiger mode devices. They either flip or don't flip to a final state based on one electron, whereas with the quantum image sensors using a multi-bit mode, we can actually determine photon number quite accurately in a single frame. On the other side, as I said before, we cannot get the speed that SPADs can get for things like time-of-flight imaging, at least not at this time, although I see a path forward.
Do you care to share it?
No, I don't.
Fair enough. This is, as you say, it is a field that is very much what have you done for me lately? And certainly it's not the only field where that applies. But I'm curious, everyone's been disrupted in different ways by the pandemic situation. But what are some of the current endeavors that you're pursuing? What's your work? In what directions is it taking you now?
Well, we spun off the quantum image sensor work for the most part to a startup company that I co-founded with some of my former PhD students called GigaJot, and they are proceeding nicely towards future products. At Dartmouth, we're still pursuing things like low-light imaging, trying to get to understand still what are the limitations for noise for our detection of single photoelectrons. We're currently at about 0.2 electrons RMS read noise, 0.2. So what's stopping us from getting from 0.1 or 0.05? What are the fundamental mechanisms in the silicon that are causing that 1 RF noise, residual 1 RF noise guys, for example. Still interested in high dynamic range. We can actually do high dynamic range with quantum image sensors, which seems like an oxymoron, but that's already been demonstrated by GigaJot and as shown theoretically earlier in some work that we published out of Dartmouth. Looking forward to more work on time delay integration, because once you have this big matrix of ones and zeros or multi-bit data, getting rid of motion, especially over different tracks of motion in the same image simultaneously, is something that is starting to be demonstrated with computational imaging already, something that I was pretty sure it could do, but was beyond my own skill set to figure out. It's a lot of math in there. So that's kind of exciting also. So that means that you could take low light images with relatively long exposure times with motion going on, whether it's handshake or just objects moving, and make a very clear freeze frame kind of image from that, all that data. I still want to get to a billion pixels on a chip. I can't wait for that. Totally feasible right now. We're just waiting for a customer that needs that at GigaJot. And also working to extend the wavelength range. How do we get to near-infrared, shortwave, and even midwave IR using different materials, and or out to UV and higher energy photons like X-rays, which is a different problem that we're working on with Los Alamos.
So you have quite a few pursuits that are active, and we touched on this a bit earlier. But do you find yourself often or at all reflecting on how far active pixel image sensing has come and your contributions to it? I just ask because it's not an insignificant by any means set of achievements. It's quite significant, and it's quite prominent and pronounced. Do you afford yourself time to reflect and even enjoy some of the advances that you have put your stamp on?
Well, I love shooting photos with my smartphone, for sure. I do it all the time. I even take selfies from time to time. It's easy, especially during this pandemic, and realizing how much people have benefited from being able to Zoom and kind of keep business going. Not Zoom, but any products like Zoom. It's kind of gratifying, also mind-boggling at the same time, but it's been very helpful. And then the other thing that's really come up in the past year or two, which was completely unexpected for me, is the fact that so many people have these smartphone cameras in their pocket that they can capture video under all kinds of circumstances, and they've captured a lot of things that have improved our ability to serve social justice around the world. And this is a huge impact, I think, on the human condition, and I'm very happy that I played a small role in that as well.
Yeah, that's an interesting point. It hadn't occurred to me, but it's very true. Is that perhaps the most gratifying? Because that is, not only is that a fun thing, it's not a fun thing, it's a hugely important thing.
Yeah, I find it very gratifying. Again, there's lots of technologies that contribute to that, but certainly putting a camera in every phone in everyone's pocket has made a difference there. And yeah, in the big picture of humanity, I think much more important than selfies and cat photos. Nice to feel like do some good as well.
Dr. Eric Fossum is a Queen Elizabeth Prize laureate. This year, he won a Technology and Engineering Emmy Award. He is an inductee into the National Inventors Hall of Fame. Eric, I want to thank you for joining us.
Thanks so much. It's really been a pleasure.
The European Photonics Industry Consortium, or EPIC, promotes the sustainable development of organizations working in the field of photonics in Europe. Members encompass the entire optics and photonics value chain, representing technologies spanning LED lighting, photovoltaic solar energy, PICs, optical components, lasers, sensors, and other photonic-related technologies. Joining us now are the two newest members of the board of the European Photonics Industry Consortium, announced officially at the EPIC Annual General Meeting on April 15th. Berthold Schmidt is CEO of TRUMPF Photonic Components, a developer and manufacturer of high-power infrared sources. He joins us from outside Ditzingen, Germany. And here with us as well is Adam Piotrowski, CEO of VIGO Systems, a leading developer and manufacturer of uncooled infrared photon detectors. Dr. Petrovsky joins us from outside Warsaw. Hello to you both, and congratulations to you both.
Thank you, and hello. Thank you.
I'll start with you, Dr. Petrovsky. Your appointment to EPIC's board, paired with your current position, creates a platform for both of you to establish new and enhanced opportunities for photonic stakeholders. And I want to ask you, Adam, first, how do you plan to use that platform to do just that?
Doing business is all about connections and networking, and actually EPIC is doing a great job recently in this very hard times. Number of new members, number of participants of the technological meetings seems to prove that we are creating a photonic society based on relations, based on knowledge. And myself, as a CEO of the Polish company, would like to be a part of this society and use this opportunity to grow our business, to help others solve their problems, provide solutions. And we see lots of local opportunities in Poland where we can collaborate in the partnerships across the Europe, across the globe, working with other companies, universities to introduce photonics technologies to a current typical industries. So that's really a good occasion for a Polish company, seeing and also a drawback of the European and local system to improve the way we can work and introduce new technologies. We saw for last few years a great job done by European Commission with founding the European projects on research and development for solving a critical issues for the society. So that's a good point. Let's use the photonics and solve the problems.
It really is a wide network for all stakeholders. You mentioned industry, academia, government too. Same question to you now, Dr. Schmidt.
Yeah, thank you for that. And I can only agree. I mean, we see this naturally from TRUMPF as I would say, one of the larger companies in the photonics industry with 1.2 billion euro in revenues, from a slightly different angle. But I think for us, the photonics industry per se as a network is very important. And if I see myself as a former CTO of the laser division and now CEO of the TRUMPF Photonics Components group, I think I have a good insight into the technical trends of our industry and in particular also the needs of our customers and the international business development of multiple corporations. But on the other side, let's be realistic. In this diverse, fairly complex and then connected industry, you never have the full and most actual picture. And I think in that way, the EPIC is a perfect platform to stay connected and informed about the latest trends in technology and industry. And to me, combining both the TRUMPF laser world and the connected EPIC association, I think will generate further synergies to strengthen the European photonic community. And that's, to me, very important. And that's what I want to contribute to.
You mentioned the size and the reach of TRUMPF, the name recognition of a brand like TRUMPF. Dr. Schmidt, how does TRUMPF and EPIC align? And you touched on this a moment ago, but how does the company and EPIC, the company and the consortium, align to grow the photonics industry? You talk about sort of fostering what's there, but how does this relationship help grow photonics in Europe and worldwide?
Yeah, I think we have very similar interests. The one naturally more from a private business perspective, and the other one more as a European platform. But in general, we both have high interest to drive the photonic industry forward, connect to science centers, institutes, universities, develop new talents in this industry that help us to bring the most actual technologies to the market. And on the other side, European or EPIC is a European platform that allows companies such as TRUMPF to access to these people and to connect to them. And therefore, I think we have very, very similar interests, and that's to me a perfect match. And that's also why I'm very happy to contribute and support EPIC in the future as a board member.
And Dr. Petrovsky, I'll get your thoughts on that question as well.
My company, VIGO Systems, is a provider of components, infrared detectors. Sometimes we integrate them with sources, and this is a creation of foundations that others could use for developing devices, systems, and integrating them into the application. So it's critical that those solutions are validated by clients to check if they met their objectives. And inside of the Photonic Society, we have lots of different levels of companies, starting from materials, optics, active elements, devices, systems, and working together on the technological roadmaps, discussing about potential applications and solving the problems of current applications. That's a great alignment between mid-sized company as VIGO and the largest photonic industrial association. I love being part of it.
The European Photonics Industry Consortium, EPIC, announced officially at its annual general meeting on April 15th 2 new board members. They're here with us now on All Things Photonics. Berthold Schmidt is CEO of TRUMPF Photonics Components, and Adam Piotrowski, CEO of VIGO Systems. Adam, I'd be remiss not to ask, we're emerging now from a 1+ year pandemic, and for a mid-sized company such as your own, what's in store from your perspective for the global photonics community looking to the future?
The role of photonic is to sense more, to see all, to interact and communicate. That's what we do every day with our product. So we hope that we could continuously be a part of protecting societies against threats, to introduce new photonics ways to sense human body signs, to improve the quality of manufacturing, to automatize the manufacturability of different processes. So that's really our job is to integrate more functions into the products, to make the device smaller, more sensitive, more specific. So having the knowledge about the threats around us, it's a key solution to the future global pandemic. So hopefully we could introduce all those technologies to everyday human lives and make the world better.
You talk not only about the reach of optics and photonics technologies, but you talk about the diversity that the field encompasses. Berthold Schmidt, turning to you now, I want to get your thoughts on that as well, but also, it occurs to me, we've learned quite a lot about collaboration and the need for collaboration as it pertains to the role of optics and photonics in the last 14 months. Is that a fair assessment?
Yeah, absolutely. As Adam already stated, the world has accelerated in terms of the digitalization of the society. And I would say even the world society, it's not just the Western world or the industrial world. We see a general trend to an accelerated digitalization. So the use of handheld devices increases. In particular, laptops have seen an increasing demand. Customers become more demanding related to camera and video signal quality. I would say virtual reality meetings become more popular. I see this with my kids, how they're more or less living partly already in a virtual world. And there is another trend that I observe maybe during the last 2 years already. It's this revolution in powertrain technology, a trend towards more and more electrified transportation. And I think that's something both consumer electronics and production of e-batteries. This leads to an accelerated introduction of advanced photonic production tools, which is kind of a key product platform for the TRUMPF organization, but as I also know, for multiple other companies within the European environment. And that is a very positive trend to our technology and to our industry. I see this very positive. And if we manage to establish if you allow me that, an integrated value chain in Europe, then including the final production locations, that would be naturally fantastic and a very strong push for the European photonic industry. And I think that's what EPIC should to push for.
The EPIC annual general meeting was held on April 15th. Upcoming events for EPIC include the EPIC online technology meeting on laser micromachining on the 17th of May, as well as the EPIC online technological meeting on VCSEL manufacturing and applications. That's on June 7th. The EPIC annual general meeting 2022. Dates are yet to be announced for that, but they'll be announced soon. The two newest board members of EPIC, Dr. Adam Piotrowski and Dr. Berthold Schmidt, joining us here on All Things Photonics. Thank you to you both, and congratulations.
Yeah, thank you, and thanks for the interesting questions. Thanks a lot.
That does it for this episode of All Things Photonics. Thank you to our engineer, Alan Shepard, and to Joel Williams with the news. Our featured music is courtesy of betterwithmusic.com. Most of all, thank you, our listeners. As always, you can share your thoughts, pitch us ideas, let us know how we're doing. You can reach us at allthings@photonics.com. All Things Photonics is available on all major platforms, including Spotify, Apple Podcasts, as well as on our website. Subscribe, never miss an episode. I'm Jake Saltzman. This has been a Photonics Media production.